Now I have to acknowledge, I guess probably everybody's brain's a little tired now because there's a lot of meat in what we're trying to accomplish with the system designer. Now I can assure you it's not just for communications. As I said, we are very focused on high-speed signal processing communications, but the LabVIEW system designer will solve a lot of applications in the future. Imagine any application that has multiple pieces of hardware. Maybe you're building a machine controller with a real-time controller and a Windows host, and you're doing publish and subscribe over Ethernet. That's an asynchronous connection. Imagine any system from a single PC with one board to racks and racks of PXI equipment. So imagine the benefits of graphically being able to see your hardware components and see the configuration. And of course, as you've seen over and over and over, whether your application is control or data acquisition or test or communications, when you're building and using FPGA-based systems, you need tools that make it very easy to integrate all the IP you need to use, including what you're writing with LabVIEW. So clearly, we're focused on a wide range of applications. Communications is just one of those many applications. Another really important part in that last demonstration is that you used our FlexRio product. This is a very important FPGA product because it's modular. It has an FPGA baseboard and then interchangeable adapter modules so that you can swap out and meet different applications with the same basic product platform. This flexibility is really important for both you and for NI, because as your application requirements change, you or NI can build new adapter modules and use FPGAs for new applications that we hadn't thought of yet when we're building a standard product. So the last demo, the adapter module was used to acquire and generate these baseband and intermediate frequency signals. Now we'd like to show you a completely different application of FlexRio using an adapter module that allows you to do vision applications using the FPGA. So here to tell you about that are Jeff Kennedy and Steve Tang. Hey, Steve.
Hey, Mike.
So tell us about how FPGAs are going to change the way we do vision applications.
Yeah, we're really excited about the way that FPGA is going to be able to address the applications in our area. We can use FPGA for robotics and guidance applications to enhance images or select a region of interest. We can also use FPGA to speed up the overall system performance in medical applications by using it as a preprocessor or a coprocessor. And the area that I'm most excited about is the capabilities of FPGA for control and synchronization for applications like high-speed sorting as well as laser tracking.
Cool. So what is it about the FPGA that you think is going to be really good for these control and tracking type applications?
Well, if we look at the requirements of those applications, it lines up really well with the strengths of an FPGA. Things like high data rates, parallel data sets, as well as just tight timing and control.
Cool. So can we do these kind of applications today?
Absolutely. These types of applications, we usually use a Windows or a real-time operating system to address these applications to acquire images, process, and then output the results. And we have a real-time operating system here to just show you that right now with our first part of the demo.
Okay, Jeff?
Right. So what we have for you today is a laser tracking demo that makes the use of two lasers. First, a red laser that will be controlled by hand, and a second green laser that will be controlled by our system to track the position of the red one. We have a Bosler 1.3 megapixel, 500 frame per second camera link camera acquiring the images, and a MEMS micro mirror steering the green laser provided by Miracle Technologies.
And Mike, here's the red laser for you to use.
Okay.
And so you gotta stay on the screen here. I know it's a little big.
Oh, this white screen you want me to stay in
right.
it? Okay. So you're going to track me?
Yes.
Okay, so
So
this
here
is
we
the
have
Windows
our,
application?
Yeah, so here we have our VI deployed on that LabVIEW real-time system. It's an Intel Core i7 processor. We have an NI PCIe 1429 frame grabber acquiring the images, and an R series board provides the I/O to control the mirror.
Well, it looks like it's tracking pretty well. Would you say that's useful for a lot of applications?
That's not bad, but if we were trying to track a really high-speed object, we probably wouldn't be able to keep up. And we probably wouldn't be on stage if we didn't have something better to show as well.
So you're going to be able to do this with the FPGA? Is that what you're telling me?
That's right. In R&D, we've been working on a new camera link adapter module for FlexRio. This adapter module is able to acquire from base, medium, or full configuration camera link cameras. And we also included some TTL-IO for general purpose input and output, two isolated inputs for triggering, as well as a quadrature encoder for rotational measurements as well. And as Jeff is getting the demo set up here for the FPGA version, we can see it run.
Want me to track? You going to track me again?
That's right. We're going to show the difference here.
Well, it's really hard to tell on the screen. So how's our tracking doing now?
So with this tracking, the problem is with the human eye, it's a little hard to perceive the differences between the RT and the FPGA version. But with the FPGA version, as you can see, our error is much lower than what it was before, where it was much wider variance.
Cool. So Jeff, tell us exactly what we're doing with the FPGA in this application.
Sure. So first we needed a way to bring the camera data into the FlexRio FPGA. We did that by reusing existing IP previously developed on the PCIe 1429 and brought that into LabVIEW using a clip. We next implemented the processing and control logic directly in LabVIEW FPGA. The processing logic finds the location of each laser spot and sends the results to the control logic, which uses our adapter module I/O to drive the mirror.
Cool. So specifically, what is it about the FPGA then that makes it so much more accurate?
So with the power of FPGA acquisition, processing, and control, we were able to significantly reduce the control loop latency, and that latency allows us to track the laser more closely.
Well, cool. That's a really great example of how we're also going to apply FPGA technology to other application areas like vision. Thanks, guys.
Thank you.